Hello, and a very warm welcome to you all. Today, we're going to tackle a really powerful idea in artificial intelligence, something called a Bayesian network. Now, I know that sounds complicated, but trust me, we're going to make it super simple. How? By using a story that we can all relate to, a student, their grades, and what happens next. I promise you, by the end of this, it'll all make perfect sense.
Okay, so here's our plan for today. We'll kick things off with our student's story. Then we'll look at how we can reason forward, from cause to effect, and then backward from effect to cause. We'll also unpack a really fascinating idea called the explaining away effect. And finally, we'll get into the real nuts and bolts, the rules that make these networks tick. So let's get started.
Right then, let's meet our main character. Everything we're going to talk about today, every single concept, is going to be based on this one simple story. I want you to think about this for a second. The world is, well, it's messy, isn't it? A student's performance, for example. Is it just about how smart they are? Of course not. It depends on how tough the course is, maybe how good the teacher is. So many things. There's so much uncertainty. So, the big question is, how on earth can we build a system that understands and reasons with all this uncertainty? Well, you guessed it, that's exactly what Bayesian networks are for.
Okay, have a look at this. This diagram is going to be our best friend for the next few minutes. Just think of it like a roadmap of cause and effect. See, up at the top we have D for difficulty and I for intelligence. Now look at the arrows. They both point down to G for grade. What does that tell you? It tells you that both how difficult the course is and how intelligent the student is will affect their grade. Simple, right? Then the grade, or G, has an arrow pointing to L for the recommendation letter. And one more thing, notice how intelligence also influences S, the student's SAT score. It's all connected in a logical flow.
All right, let's take this map for a spin. We'll start with something called causal reasoning. Don't worry about the fancy name. It just means we're going to follow the arrows, moving from a cause to see its effect.
So let's cook up a scenario. Let's say we have a student, and, well, we think they might not be the most intelligent student, okay? But they've been clever in one way. They signed up for a really easy course. So here's the question. What are the chances they can still get a good recommendation letter? So how does the network figure this out? It's a very logical step-by-step process. First, step 1. We tell the network what we know for sure, our evidence. In this case, that the course is easy, or D0. Got it? Okay. Step 2. We add our belief that the student has low intelligence, which we'll call I0. Now for the clever part. Step 3. To find the probability of a good letter, that's L1, the network doesn't just guess. It crunches the numbers for all the possible grades and SAT scores that could happen in this situation and adds them all up. It's like exploring every possible future to give us one single, powerful answer.
And voila, the answer comes out to be 0.513, or to put it simply, a little over a 51% chance. Now this is the important part. Think about what this means. Even though we started by thinking the student wasn't very smart, just one thing, the cause of an easy course, had such a big effect that it actually made a good recommendation more likely than not. See? We reasoned forward, from cause to effect.
Excellent. Now let's flip the script. Let's put on our detective hats. What if, instead of starting with a cause, we start with an effect and try to figure out what caused it? This is what we call reasoning backward, or evidential reasoning.
Okay, first, let's set a starting point. Before we know anything at all, let's say we assume there's about a 30% chance that any given student is highly intelligent. Okay, so P of I1 is 0.3. Now, we get a piece of evidence. We find out this student got a C grade, a bad grade. Now watch this. The moment we plug that information in, our belief that the student is intelligent just crashes. It goes from 30% all the way down to about 8%, or 0.079. We saw the effect, the bad grade, and that let us reason backward to update our belief about the cause, their intelligence.
Okay, now for my favorite part. This is where these networks get really clever. We're about to see how just one more piece of information can totally change our conclusion. This is a brilliant idea called the explaining away effect.
So, let's pick up where we left off. We know the student got a bad grade, and right now we're thinking they're probably not that intelligent. But what if someone else comes up to you and says, that course was brutally difficult. Everyone struggled. Now we have a new clue, a new piece of evidence to consider.
And this is just fantastic. Remember, with only the bad grade, our belief in the student's intelligence was way down at 0.079. But now we add this new fact,
The course was difficult, and look what happens. The probability actually goes up to 0.11. Now, it's not a huge number for sure, but the point is it went up. Our belief got stronger. So why? Why would that happen? It's because the difficult course gives us another reason, a powerful alternative explanation for why the student got a bad grade.
You see, our brain does this automatically. We think, oh, wait a minute, maybe the student is actually smart and they got a bad grade just because the course itself was ridiculously hard. That's it. That is the explaining away effect in action. One cause, the difficult course, explains away the bad grade, making the other cause, low intelligence, seem less likely.
Let me give you a very common Indian example. Imagine your internet is working very, very slowly. What's your first thought?
Arey yaar, this router is useless. I need a new one, right?
You blame the router. But then you look outside and you see the power is out for the whole neighborhood because of a huge monsoon storm. Suddenly, are you still blaming the router? No. The power cut explains away the slow internet. It's the exact same logic.
So you have to be wondering, how does the network do this magic? How does it know what's connected to what? Well, it's not magic. It's all about a set of very clever rules that are built right into the structure of the network itself.
Let's go back to our roadmap for a second. Look at the recommendation letter, L. The only arrow pointing to it comes from the grade, G. Now let me ask you a question. If I tell you a student got an A in the class, do you really need to know their SAT score to guess if they'll get a good letter? Probably not, right? The A tells you pretty much everything you need to know. It's like the grade, G, creates a roadblock. It blocks any information from the SAT score, S, from getting to the letter, L. And in nerdy terms, we call this conditional independence. And this idea leads us to the most important rule of all, the one that makes these networks so efficient. It's called local independencies. And all it says is this: any node on this map only really cares about its direct parents, the ones with arrows pointing right at it. Once you know what the parents are doing, you can forget about the grandparents, the great-grandparents, everyone else. So the grade only cares about intelligence and difficulty. That's it. This one simple rule stops us from having to do a crazy number of calculations, and it's what makes the whole thing work in the real world. And of course, for any of this to be useful, our map has to be a good map. It has to reflect reality. We have a special name for a good map, an IMAP, short for independence map. It's just a way of saying that the connections and roadblocks we draw on our map are actually true in the real world. If our map tells us something is independent when it's not, well, then it's a bad map. The map must not lie.
Okay, so let's bring this all together. Why have we been talking about all this? Because this isn't just some academic theory. This is a massively important tool for building real artificial intelligence.
So, why did we go on about all those rules, like local independencies? Here's why. Because those rules are the secret ingredient that makes these networks actually work. By breaking down a huge, complicated problem into small, local pieces, we make the calculations way, way simpler. And that means we need less data, the computer has to do less work, and the whole system becomes faster and more efficient. It's how we go from a neat idea on a blackboard to a powerful AI system that can actually solve problems.
So if there is one thing I want you to remember from today, it's this. That graph we've been looking at, it's not just some random diagram. It's a picture of our assumptions about the world. It's us drawing out how we believe things are connected, what causes what. Building one of these networks is really an exercise in thinking clearly and logically about a problem.
Today, we use the story of one student, but this way of thinking, this idea of mapping out causes and effects when things are uncertain, you can apply it to literally anything. So I'll leave you with a question to think about. In your own world, in your studies, your job, maybe even your life, what are the hidden connections? What's really causing what? Try to map it out. Thank you so much for your time today.